In this lecture, we are going to continue our discussion on how to optimize a portfolio. Previously, we looked at a simple problem where we wanted to take a set of assets and find the maximum and minimum possible return of any portfolio containing these assets. We found that this problem could be solved using linear programming. Of course, those portfolios didn't take into account risk. In this lecture, we will consider how to optimize a portfolio in terms of risk and return simultaneously. Note that there is an inherent trade-off in portfolio optimization. We know that as expected return goes up, so does risk. So it's not possible to say, give me the maximum return but the lowest risk. As long as you want to increase your return, you have to be willing to take on more risk. Portfolio optimization is all about not taking any more risk than is necessary. We've seen examples of suboptimal portfolios. For example, consider these 2 points. They both have the same risk, but one has higher return. Obviously, if you are willing to take on this amount of risk, it's better to obtain the highest amount of return possible for that level of risk. Now consider these 2 points. They both have the same return, but one has less risk. Obviously, if we really wanted to have this expected return, we will choose the portfolio with less risk. There's no reason to take on more risk than we have to. So that's the idea behind portfolio optimization. We want to trade off risk and reward, but we don't want to take on any more risk than necessary, and we also want to maximize our reward for a given level of risk. As you recall, the way that we measure risk is by standard deviation. In this lecture, we will focus on variance because, as you know, this gives us a nice quadratic function, which is typically easy to optimize, find the gradient of, and so on. Also, since the square is a monotonically increasing function, if we've minimized variance, we've simultaneously minimized the standard deviation. Alright, so knowing what we know so far, this problem is quite easy to formulate if we make some assumptions. Let's assume that our objective is to minimize risk, or in this case, variance. That is, we want to minimize W transpose sigma times W with respect to W. Let's also assume that we would like to achieve a specific expected return on our portfolio. So we have the constraint that mu dotted with W is equal to R, some desired return. Furthermore, we still have the constraint that the W's must sum to 1, which makes our portfolio a valid portfolio. Finally, we may have some additional constraints, like all the Wi's greater than or equal to 0 and less than 30%. You will notice that this problem is very similar to our maximum and minimum return problem. It's still a constrained optimization problem. We still have the same constraints for the most part, with one additional linear constraint for the desired return. But the main difference is that the objective function is now quadratic instead of linear. In fact, when we have a quadratic objective with linear constraints, we call this a quadratic program, or QP for short. Now, unfortunately, there is no function in SciPy for quadratic programming. This is very strange because there is a quadprog function in both R and MATLAB, so it seems appropriate for SciPy to have one also. So what can we do about this? Well, there are several options. One option is to use a library called CVXOpt, which is a library for convex optimization available in Python. We will not focus on this option, although you may come across an example or two. The second option is to stick with SciPy and use a generic optimization function called minimize. Technically, this is suboptimal because it's designed for generic functions. If you know your problem is a QP, then you can use more specific algorithms to solve the problem using its structure. So we would expect the performance of CVXOpt to be better, since that handles quadratic programs explicitly. However, using SciPy is easier because you don't have to manually determine all the matrices to pass in to your QP solver. Later, we will look at another optimization problem for maximizing the Sharpe ratio, which does not have an obvious linear or quadratic structure, so it's nice to have a generic optimizer like minimize, which can handle anything. So for this reason, we will focus mostly on using minimize, which will require a bit less thinking about the implementation. And also, you don't have to install cvxopt, which is probably less familiar to you than SciPy. Before we move on to the code lecture, I want to give you a brief rundown on how the minimize function works. The first argument to the minimize function is a function. This is the function that you actually want to minimize. For us, this will be the variance. So if you have a function that takes in a set of weights for your portfolio and returns the variance, that would be exactly what you need. The second argument to the minimize function is x0, which represents the initial guess for our weights. We will use the equally weighted portfolio, which is just a uniform distribution over each asset. The next relevant argument is method. SciPy's minimize function can use different optimization algorithms, but we will be using one called SLSQP. This stands for sequential least squares quadratic programming. Now, don't be fooled by the name. This is still a generic optimizer. The next relevant argument is the bounds. This works exactly the same way as it did for the linprog function. So you can pass in a list with d items, and each item will be a tuple containing the upper and lower bound for that element. Finally, we have the constraints argument. We'll get into this later in the code lecture, but basically this is represented as a dictionary or list of dictionaries, where each dictionary holds a constraint. You can either tell it to be an equality or an inequality constraint, and then you can pass in a function that returns a specific value to tell SciPy whether or not that constraint is met. Now, I want you to pay attention to the fact that this does not require you to pass in any specific matrices or vectors, like the covariance or mean return vector. All you're doing is passing in functions. This means that SciPy doesn't know what the parameters of your problem actually are, which on one hand makes this easier for you to write, but on the other hand makes it less optimal than using a QP solver directly.